Hi, my name is Carlo Giacometti, and today I will talk about applications about understanding speech with the Wolfram language. Hello everyone, my name is Carlo Giacometti, and I work in the signal and audio processing team for Wolfram. And today I will talk about speech. So there is a very pretentious title that says understanding speech. So maybe that is a bit overreaching, but I will tell you what you can do with the Wolfram language to do some machine understanding of speech signals. So I'll show several example applications. One will be keyword spotting, then we'll have some speech recognition, some speaker recognition, and some gender classification. So let's start with keyword spotting. What is this problem? We have a collection of recordings, and in each of these audio signals, a person speaks a digit from 0 to 9. Well, this is completely wrong. Sorry about that. So we're using the spoken digit commands dataset that we have in our research system. And these are some examples of the data.
9, 4, 0.
Etc., etc. So we want to develop something that takes as an input these audio signals and outputs which digit was spoken. We make sure that speakers in a training test set are not intersecting with the speakers in the testing data, so we don't cheat. The classes of this problem are, as I said multiple times, the digits from 0 to 9. And if we look at the durations of these signals, they are all between 0.5 seconds and 1 second, which is very convenient in the fact that the network will always have this uniform kind of input. So we have several strategies that we could follow. We could go the completely automated machine learning strategy by using the classify function. First of all, we need to massage the data a little bit to make it in a format that makes classify happier. We define a net encoder, which transforms our audio objects into matrices, in this case of a fixed dimension. And hopefully this will capture most of the important information. And then we just throw this data inside classify with minimal effort. And this minimal effort result already gives us a 70% accuracy on the test set. And this, as I said, was really zero effort. Now, if we want to put a little bit more effort into it, we could consider defining a neural network. And since we're talking about audio, which is inherently a variable length problem, we will use a recurrent network that is based on gated recurrent layers. Stuff that works very well with sequences, essentially. We will use the same encoder. We will compute the MFCC features to feed into the network. So, again, the encoder is defined. You can see the network is really simple. It just involves 2 gated recurrent layers and then some basic machinery to do the classification between the various digits. I will actually train it here, and hopefully everything will work. And yep, this is just running in real time on my machine. My machine does not, neural network does not exploit a graphics card on my machine. So everything is computed on the CPU. And even with that, the training speed for this simple example is quite impressive to respect to what we could have had in the previous versions. And after the training is done, we can compute the performance. And as you can see, we jump from a 70% accuracy to a more than 90% accuracy. One interesting thing that we could do is some feature extraction using this network. So instead of classifying, we want to, from an audio signal, we want to extract a single vector that is semantically meaningful to what the input was. So what we do is we chop out some layers from our network that we originally defined, that we have trained, As you can see, I took out the last layers that did the classification. So this produces a vector of 64 elements, independent of the length of the input. And we can use feature space plot to visualize all of the testing data. So what a feature space plot does, it takes these length 64 vectors per each input and tries to place them in a two-dimensional space in a meaningful way. And as you can see, it does cluster signals with different numbers in the appropriate way. They are colored, in addition to the labels, they are colored, each digit is colored in a different way. So this way we can extract some information that is not just the classification, some vector that encodes semantic information about the signal. So we can now move on to a much more complicated task, speech recognition. In version 12, we are introducing, as you might have seen from Steven's demo, we are introducing the speech recognize function. And what does it do? I mean, as advertised, it takes an audio input, this audio input.
Right then, perfect timing.
And tries to figure out what was spoken. The operation is comprising two parts. First, there is an acoustic model that transforms the audio signal in a sequence of probability distributions over characters. And then there is a decoding step that might or might not involve a language model. A language model takes the raw output from the acoustic model and tries to correct it with some knowledge about the language. By the way, this, at the moment, only supports English speech. It will not immediately support any other language, in version 12, at least. So we can actually look at the internals of this function. The acoustic model is the Deep Speech 2 network that was released by Baidu. And we are using this pre-trained network because they managed to train it on an internal data set that they have that we do not have access on, but it has almost 10,000 hours of label speech. So what goes into this? The audio object is encoded in a spectrogram, and this is how the encoded spectrogram might look like for our specific signal. And then is fed into the network. The network has a few convolutional layers at the beginning that are followed by some custom Gauge recurrent units that do most of the work. So here we go. This is the raw network that just grabs the spectrum as an input, and it outputs per each time frame the probability distribution over all characters. So we can look actually at this result. Let me make this plot slightly bigger. So this is the probability per each character over time of our signal. This result is then processed by a CTC beam search. So what we're trying to do is we're trying to find what is the most likely sequence of characters given this result of the acoustic model. So the number of possible sequences, of course, there are a lot of time steps, is very high. So this is essentially combinatorial hell. We want to avoid that. So what happens at every step, the decoder figures out all of the possible continuation and then keeps only the first n. And these get passed at the next step. So at each step, we only compute a limited number of options. And you can see, whoops. You can see these are, on the vertical axis, you have the coding step. And on the horizontal axis, you have the various choices of decodings per those times. So you can see how they evolve And then this is the final result by the acoustic model, decoded by the CTC beam search. Now, if you remember, the third result that I gave with speech recognize was much better than this weird sentence. That is because this output is then filtered by a language model that takes into account knowledge about the language that was spoken. So again, this is a modified beam search decoder. So we have our probabilities out of the acoustic model. The dimensions, the second dimension of this matrix is 29. This is the number of classes that we are considering, which are the characters from this alphabet, plus a blank character. So our language model is based on a character-level language model that was trained on data sets of transcripts of TED Talks. We are planning to upgrade this. It will probably be upgraded before version 12 ships, but at the moment, this is what we have. This is a character-level language model that is based on recurrent layers. Some surgery is required to massage this network into something that is more efficient in batch evaluations for the beam search computations. And some more massaging is necessary for the output of this network to be included in that computation. So we end up with this object here that contains all of the language model itself and all of the information that is necessary for the language model to play nicely with the beam search. And here I am exposing very much internal code that is, of course, liable to be renamed, deleted, modified, et cetera, et cetera. At each step, what happens is the CTC beam search has the probability from the acoustic model, and it computes what is the probability of that sequence according to the language model. And these two probabilities are mixed together using a mixing function that will be controlled by this mixture level parameter. And this will give us a score of the result that will take into account both the acoustic and the language model. So you can see these are the first 4 top results. And you can see that that spelling mistake that the main network made is now corrected by our language model. So another thing that this is more of an application example. This will not have any associated function in 12, but this is an example of what the Wolfram language can achieve combining the audio processing capabilities with the neural network capabilities. So I want to show a different problem, speaker recognition. So we don't want to understand what was spoken, but we want to figure out who was the speaker. To tackle this problem, of course, as with all neural networks projects, we need to start from a data set. Here, the Vox Celeb2 dataset was used. This is a collection of about 1 million utterances by about 6,000 speakers. And the structure of this dataset is pretty simple. It has, per each file, there's associated some information about who the speaker was and what gender he or she was. And the labels are, of course, the identities of these people. You can see some example here. The task is very well defined. It's a very simple classification. The classes are mutually exclusive. Of course, there can be only one speaker per file. So the network that we chose to use is actually a network that is generally used for image processing. It's the MobileNet version 2 network. So this accepts only a fixed size input. So how do we solve the problem of variable length input that is, natural with these signals? So we compute our feature, which in this case will be the Mel spectrogram. This produces one single big matrix. What we do is we chop it up in fixed size chunks that are overlapping, and then map the network over each of these chunks. So let's see how that works. So this is the encoder. This is the result from the encoder. As you can see, this is two fixed size matrices that will then be fed to the main network. And, whoops, let me just reevaluate this one. Here we go. This is the main network, as I said, fixed size input, and then a single vector of length about 6,000, which will give us our classification. So we can apply it. Wait, just a second. Sorry about that. We will apply it on each of our frames, and then we don't really want a result of variable length. So we need to aggregate the result over the time dimension. So we take the mean, and this is what happens here. We take the mean of the result, and then we feed this the mean of the result to the decoder, which will then give us the final classification. So what we have done, we have classified, we have a network that takes an input and tells you which celebrity you might sound like. Pretty useless, right? Not particularly interesting. But what the network learns is how to differentiate voices. And this is a really powerful skill. So what we can do, we can go back to what we did before with our digit recognition. We take the network, we chop the last part, and we then produce a meaningful semantic embedding of the input signal. So I will go back to the spoken digit command. And as I said before, this dataset does have some information about who the speaker was. Again, I will import the network. And as before, if we just use the network, this will just give us the probability that you sound like some celebrity. But what we can do, we can grab just the first layer of this network, which is the mobile net in this case that was trained, and produce something that doesn't classify anything, but produces this semantically meaningful embedding. And if we apply that to our digit dataset, if we apply that to our digit dataset, we can see that in the feature space, the various speakers are very much separated. So this network now, we can see that this network understands information about different voices and is able to encode this information about voices in one single fixed length vector. So I have another example that does essentially the same on a different data set. So I will not go completely through it. I will just show you the results so I can show you the last example. This is, by the way, this is the same structure that I just showed you. It's just applied to the test subsection of the Vox Celeb dataset. The network, again, has not seen these examples during the training. And it still manages to separate quite effectively different speakers. This dataset is more representative of what you would get in the wild rather than a very much curated dataset like the spoken digits one. So the last application I want to show you is gender classification. So as I mentioned before, in the Vox Celeb dataset, we do have information about the gender of the speaker. So what we did in this last example is just, again, some massaging of the data where the label is not who the speaker was anymore, but what the gender of the speaker was. Now, one approach is to take an unevaluated network and start the training from scratch, hoping that the network will learn how to differentiate the genders. But we do have a network that, as I said, understands something about voice. So we use that network, as we did in the previous examples, as feature extractor. And we can build on this pre-trained voice-related feature extractor to just call, in this case, just classify. We're not even bothering defining a new neural network. So what happens for the data is then encoded by our trained network and then classified using, just classify without any bells and whistles, just minimal effort going into this. And even with this minimal effort, we managed to get 96% accuracy on the test set, classifying the gender of the speaker. And you can compute this on whichever audio signal you might want. Okay, and this concludes, I guess, the collection of examples that I want to show you. Thank you very much. This is the team that worked on the, I want to thank specifically Rebecca and Timothy, that were the ones that did most of the work for the speech recognize function, and this is the rest of the signal, image and signal processing team. Thank you very much.